Hello students, in this section we are going to look at substitution in triple integrals. So you have a region in the UVW space and you have another region in the XYZ space. So under suitable transformations, the region in the UVW space is transferred to the another region in the XYZ space, and integrals over the XYZ space can be computed using integrals in the corresponding UVW space. So that is the idea. So in triple integrals, dv comes into picture, but dv in XYZ space is dx dy dz, and when it is transformed to the UVW space, the corresponding volume element dv is not just du dv dw, it is something more. It is Jacobian times, as in the case of double integrals. So we will discuss the scenario in detail. So suppose I have XYZ space. X-axis, y-axis, z-axis, and the region is denoted by D in the XYZ space. And suppose you have a real valued function f. This is the real line. This is your function f, defined over this domain D, and suppose you have a bijective, and that means 1 and 1 transformation from the XYZ space to the UVW space. So this is U axis, V axis, W axis, and suppose the corresponding domain D is transformed to, let us say, this region called G in the UVW space. That means for each point x, y, z here, I have a corresponding point u, v, w in G. So how do I go from D to G? Similarly, I should be able to go from G to D also. So by means of a transformation. So the transformations are given by x is equal to g of u, v, you can go from here to here. Similarly, I can go from here to here. So the transformations are x is equal to g of u, v, w, y is equal to h of u, v, w, and z is equal to, let us say, k of u, v, w. This is the transformation, and this transformation is bijective, and from G to D this transformation is differentiable, and from D to G also this transformation is differentiable. That means all the partial derivatives of all the variables x, y, and z with respect to u, v, w exist and continuous, and the other way around. That means all the partial derivatives of the variables u, v, and w with respect to the variables x, y, and z, they also exist and continuous. Now look at the composition. So the composition is, so here f of x, y, z, but the composition here becomes f of what is x? G of u comma v comma w comma what is y? It is h of u comma v comma w comma, and what is z? It is k of u comma v comma w, f of the whole thing. So this is the composition, and you have a result which I am going to state as a theorem. Its proof is not in the syllabus. It is beyond the scope of this textbook. So the theorem says triple integral over d capital F, the function f of x comma y comma z, dx dy dz. This element is precisely the element dv. So it's not divided by this element. It will be denoted as dv. F of x comma y comma z dv is equal to triple integral over g, triple integral over g capital F of g of u v w h of u v w k of u v w into dv here comes, but that dv is not simply du dv dw. It is something else. It is modulus, absolute value of the Jacobian. So it is denoted as j of u comma v comma w times du dv dz. Well, what is j? It's called the Jacobian. Of the transformation. Of the transformation, and Jacobian, the definition is j of u comma v comma w equal to determinant dou x by dou u, dou x by dou v, dou x by dou w, dou y by dou u, dou y by dou v, dou y by dou w, and dou z by dou u, dou z by dou v, dou z by dou w. So this determinant is called Jacobian, and its absolute value has to be taken for that integration purpose. Okay, we will see an example. Find the Jacobian for the transformation. X equal to r cos theta, y is equal to r sin theta, and z is equal to z. So the answer is Jacobian. So here the new variables are r, theta and z. Recall this transformation is actually in the cylindrical coordinates. X, y and z are represented in terms of r, theta and z. So this is precisely cylindrical coordinates. So the Jacobian is determinant dou x by dou r. It is cos theta dou x by dou theta. Dou x by dou theta is minus r sin theta, and dou x by dou z. Dou z is 0. Dou x by dou z is 0. Now dou y by dou r, it is sin theta. Dou y by dou theta, it is r cos theta. And dou y by dou z is equal to 0. And dou z by dou r, it is 0. Dou z by dou theta, that is again 0, and dou z by dou z, it is equal to 1. So this is what it is going to be. So it is equal to r cos square theta I'm sorry. Let me erase this part. So this is equal to cos theta into r cos theta minus 0 plus r sin theta into cos theta minus sin theta minus 0 plus 0 into something. So what will be the answer? So finally you will get r cos square theta plus r sin square theta. So it is precisely r. The Jacobian is going to be r. So do you remember in triple integrals, when transferred from x, y, z coordinates to the r, theta, z coordinates, dv element in the x, y, z coordinates, which is simply dx dy dz, that is transferred to r dr d theta. So where does that r come from? That r is precisely the Jacobian of the transformation. Okay. We will do one more example. Find the Jacobian of the transformation. Find the Jacobian of the transformation. X is equal to, so it is in the cylindrical coordinates, x, y, z, spherical coordinates. X is equal to rho sin phi cos theta. X is equal to rho sin phi cos theta. Y is equal to rho sin phi sin theta. And Z is equal to rho cos phi. So answer, Jacobian of rho phi theta is equal to determinant dou x by dou rho dou x by dou rho dou x by dou phi, dou x by dou theta, dou y by dou rho, dou y by dou phi, dou y by dou theta, and finally dou z by dou rho, dou z by dou phi, dou z by dou theta. Doesn't matter if you write the first row as the first column, dou x by dou rho, dou y by dou rho, dou z by dou rho, like that, because determinant of a matrix equal to determinant of its transpose. If you interchange two rows or columns, the determinant is not going to be changed. So this is equal to determinant dou x by dou rho, it is sin phi cos theta, dou x by dou phi is rho cos phi cos theta, and dou x by dou theta is, oh, there is no space here, let me remove this line. Dou x by dou theta is minus rho sin phi sin theta likewise you find all the entries, and finally you will get the answer to be, I am not going to spend time on this, it will be rho square sin phi, rho square sin phi. So the point is that, do you remember when we computed triple integrals using spherical coordinates, initially the problem might have given in the xyz coordinates, and then you must have transferred the problem into xyz coordinates. Then that time it was mentioned that the volume element dv is dx dy dz in the xyz coordinates, but it is not just d rho d phi d theta in the spherical coordinates, it is something else. What was that? dv was rho square sin phi d rho d phi d theta, and what was that rho square sin phi? That is precisely the Jacobian of the transformation. So these two are special cases. These two means the cylindrical coordinates transformation and the spherical coordinate transformation. They are some special cases of substitution in triple integrals. Thank you.